Okay, so we have one more piece to do here for these notes. We got 3 more problems. Now, number 8, f of x equals 2 times parentheses x minus 2 to the third, and then times x plus 1/2. Think of that as being to the first, that factor, and then x minus 3, that factor is to the first power. If I count my exponents, 3, 4, 5, my lead term, so my lead term is going to be x to the 5th. So if I were to multiply all of this out, which would take a long time, it would be x to the 5th. Also, this 2 is in front. So it would be 2x to the 5th would be my lead term. So here's the deal. X to the 5th, it's an odd degree. If we plug a negative in and raise that to the 5th, it's going to stay negative. So the end behavior is going to be going down like this as x goes to negative infinity. On the right side, if you plug a positive number in, you're going to get a positive when you raise it to the 5th. Times 2 is a positive. So we're thinking something's going to look like that. All right. Now there's going to be a lot of stuff going on in between, especially with these factors. Okay, so we've got our factors, x minus 2 to the third, x plus 1/2, x minus 3. The zeros would be, this would be a positive 2. Okay, to make this equal to 0, you'd plug in the opposite of this value. So x minus 2, the solution, the 0, would be at positive 2. Here it would be negative 1/2. And here it would be positive 3. 3 minus 3 is 0. Negative 1/2 plus 1/2 is 0. Okay, so in terms of our graph, we know where the zeros are. So positive 2, negative 1/2, so here's negative 1. I'm going to put negative 1/2 right there. And then positive 3. We also know that the end behavior to the left, so after this 0 here, going to the left, it will look something like that. And then after the last 0 at 3, we're going to be going up. The function is going to be going up. If I go to y equals on the calculator, let me just show you here. Y equals, I'll just do x to the 5th, okay, without all the other stuff. Zoom 6. Okay, now you can see the end behavior. And now what's happening here in the middle is going to be different than what happens in our function. But generally, because it's x to the 5th, this is the end behavior. And this is what we have, okay, on our picture. And just to show you, if I put a negative in front of this, whoops, I'll say negative x to the 5th, notice what happens is it's going to reflect it. So instead of going down to the left, it's going to go up. Instead of going up to the right, it's going to go down. Okay, so that's how your lead coefficient really affects everything that you're doing. All right, so the question is, what's happening here in the middle? From the left, we're going to increase. At some point, we're going to turn and we're going to come back. Now, one thing to notice is that for the factor x equals 2, x minus 2, for the factor x minus 2, the 0 is x equals 2. This is raised to the third. If this was to the second power, it would be a double 0, a double root, which means we would bounce off the x-axis. This is called a root of multiplicity 3, or like a triple root. Now this is going to behave differently. If I look at y equals x raised to the third power, x raised to the third, notice that what happens is when it hits the x-axis, it doesn't bounce back, it keeps going. But it has this little kind of turn right here, a little weird motion. So what's going to happen is we're going to see something similar here. So we're going to go up. At some point, there's a y-intercept. At some point, we're going to turn, we're going to come back. Now, it's going to take a little dip, kind of like an x to the third. It's going to hit some minimum, and then it's going to come back. So I think the function's going to look like that. Let me go to y equals. Let's type the whole thing. and let's see if we get this shape. So 2 parentheses x minus 2 raised to the third times x plus 1/2 times x minus 3. Okay, now obviously my picture is not perfect. It looks like the y-intercept's a lot higher than what I had right here. Okay, but then it goes down, it hits that little kind of turn right there, and then it comes down, and then it comes back up. Okay, so this is showing us that what we have is decent. Okay, it's not perfect. We're not trying to graph perfectly, but the thing is you can look at this and you already have an idea. You already can tell what the end behavior is going to look like. You can tell where the zeros are, and you can tell in the general shape of the graph. So that's the cool thing about looking at this. All right, now the last two here, use the graph to write the factored form of the polynomial function, including the lead coefficient. So instead of going from the function to the picture, which is what we were doing in 6, 7, and 8, can we go from the picture to the function? Now, where you're going to focus is the zeros. And we're going to work backwards. We have 3 zeros. We have x equals -5. We have x equals -1. And then we have x equals +2. Now notice that this one is a double zero, a double root. Now, how that's going to affect us, so there's the zeros. From the zeros, can you tell me the factors? What would this have had to look like before you solved it? Well, if I move the -5 back onto the left, I'd go +5. So the factors would be x plus 5, this would be x plus 1, and this would be x minus 2. And just to show you, if you're not sure about it, if I take x minus 2, x minus 2, set it equal to 0, and then I solve it, that's how I get x equals 2 for the 0. Okay, now, the x minus 2, though, that factor was for a double root. So I'm going to put an exponent squared for that. So what we've got, f of x equals, what I don't know is the lead coefficient. Is this a 1? Is it a 2? Is it a 5? I don't know that yet. I do know the factors. I'm going to copy those down. What I'm going to try to do is to get a picture that perfectly matches this, the function to perfectly match this. Okay, so we've got most of the function. All we're missing is the lead coefficient. Notice that you're given one other ordered pair. Okay, you've got 0, 3. So we're going to use that. And the idea, 0, 3, is that this is an x, y. If I plug in a 0 for x, I have to get a 3 for the y value. If I plug in a 0 for x, I have to get a 3 for the value of the function. This is kind of like what you did in y equals mx plus b, writing the equation of a line. So this is my y value. Okay, you can write it as y equals if you want. That's going to be 3. That's the outcome. A times, and I'm going to substitute a 0 for all my x's. And what we're going to do is work this out. So 3 equals A times 5 times 1. Now this is -2 squared. When I square a negative, I get a positive, so that's 4. Again, the reason why this is squared is because it's a double 0. So it's the same factor twice. It's the same answer twice. And notice this is going to be an even degree because the end behaviors are the same. They both go up. 1, 2, and then this is 3, 4. So we actually have 4 zeros. It's just you have this one twice. 3 equals A times 5 times 1 times 4 is 20. So this is 20A. To solve for A, divide by 20, and we get A equals, you can say 3 over 20 or you can say a decimal. Now the last thing we'll do here is we're going to write this down. F of x equals 3/20, and then I'm going to leave the factors like they are. X plus 5 times x plus 1 times x minus 2, that whole thing squared. If you multiply this out, it's not wrong, but it would just take you a long time to do it. The last thing I want to do here, I want to go to y equals and see how accurate is this. 3/20 okay, times parentheses x plus 5 times parentheses x plus 1 times parentheses x minus 2 squared. So when I hit this, am I going to get the same picture? How accurate? All right, what do you think? I say that looks pretty darn good right there. Okay, there's the shape, and so it looks like we got it. So this is kind of cool, because what we're doing is we're fitting the picture to the function. Okay, we're trying to create the function. Last one here, number 10. We have 3 zeros. Now notice that none of these are going to be double zeros, because each one goes through the x-axis and it keeps going. So the zeros, we have x equals -4, x equals 0, x equals +4. So the factors, if the 0 is x equals -4, then the factor was x plus 4. Now, x equals 0, the factor would just be x. And then x equals 4, the factor would have been x minus 4. So we're working backwards here. So we've got f of x equals a. We're not sure what that is yet, the lead coefficient. I'm going to put the x first. So a times x plus 4 times x minus 4. Okay? Now, here's the thing. To find what a is, I need to use an ordered pair for x and y. I'm not going to use the zeros. If I use 4, 0, the problem is when I plug a 4 in, it's going to make this 0, and then 0 times anything is 0. So don't use the zeros. You have to have a different point on the function. We do have a point, 2, 6. So I'm going to use 2, 6 for x and y. The y value is the outcome. That's your f of x. So 6 equals a times 2. So 2 goes in for the x's. Now we're going to work it out. So 2 times 6 times -2. 2 times 6 is 12, times 2 is -24. Okay, we'll finish it off. We'll divide by -24. Always reduce a fraction, so that's -1/4 is a. So that's our lead coefficient. So we're going to write the whole function, f of x equals -1/4 times x, put the x in front, and then x plus 4 times x minus 4. That's our function. This is a third degree, okay, and that should make sense because we have 3 zeros. The end behaviors are different, so it's an odd degree function. Let's go to y equals and see how accurate we are. So we have -1/4 x times, was it x plus 4 times x minus 4. Okay, we'll graph it. All right, looks pretty good. And that is the end of the notes.